everyone, today we are going to discuss about magnetic circuit part 2. Here in this class we have to discuss about induced EMFs due to magnetic circuit, then coefficient of magnetic coupling, then the terms associated with flux. The first is static induced EMF. Induced EMF induced across a conductor due to the change in flux with change in current flowing it when both conductor as well as fields are static is known as static induced EMF. The in static induced EMF, the first we consider as the self-induced EMF. Now, the EMF developed across a conductor due to change in current flowing through it is known as self-induced EMF. Self-induced EMF here means if this is a coil and in this coil when we are going to apply supply as AC supply because the AC changes its magnitude and direction both, then EMF will develop in this coil. That EMF is known as self-induced EMF when voltage V is applied across it. When the current is flowing in this circuit I, this coil will develop a resultant flux that is phi. The magnitude of that phi will be equals to Ni upon S as we have discussed in earlier slides. Now S is equal to L upon mu A, where L is the length of the conductor, mu is the property of the material or permeability, A is the cross-sectional area of the conductor. Then putting the value of S in this equation, then we can easily find out what is the magnitude of phi is. Now according to Lenz law, we know the EMF developed across a conductor is given by minus of N d phi by dt. Here d phi by dt is the rate of change of flux linkage, where N is the number of turns. In this case, we are considering these are the number of turns. When current is flowing in this circuit, the flux will develop over here, and the rate of change of this flux with respect to time with the variation in this magnitude of this voltage, the EMF will develop. The magnitude of this EMF depends upon N and phi, and by the definition we know phi is equal to Ni mu A upon L. Putting the value of phi in this equation, then we can differentiate this function taking the constant term out, then it will be n square mu A upon L di upon dt. It means the magnitude of E depends upon rate of change of current. The rate of change of current, the rest of the component is constant, and hence this component can be represented with the common term. That term is known as inductance. Is the proportionality constant, also known as self-inductance of the circuit or the coil. It is represented by L, and hence in other way E can be written as E is equal to minus L di by dt, where L is equal to this component. The induced EMF and the self-inductance varies with the square of the number of turns of the coil, and on comparing first and second, we can say from this equation E is equal to this equation can be written as this minus of dn phi upon dt. Similarly, this equation can be written as minus of d upon dt Li. Now comparing these two equations, Li must equals to n phi, and rearrange this equation, we can find out L in terms of phi n and I, where H is the units, is Henry of inductance. A circuit has an inductance of 1 Henry if an EMF of 1 volt is induced in the circuit when the current varies uniformly at a rate of 1 ampere per second, and hence we can describe what is the value of the 1 Henry is. Now similarly, earlier we discussed about self-induced EMF. Now we consider the mutually induced EMF. Mutually induced EMF here means when one coil is energized by electrical supply, then EMF will develop in the nearby coil or conductor when placed in the vicinity of the magnetic field. Here it is E1 is the self-induced EMF, whereas E2 is the mutually induced EMF. In case of self-induced EMF, we know E is equal to minus of N d phi by dt or minus of L di by dt, whereas in case of mutually induced EMF, the L is replaced by M and the current is I1. Because the EMF developed in this coil, it is because of the current in this coil. Let this current is I1, and considering this I1 current, this we can find out the rate of change of flux. Let this current is I1. Because of rate of change of this flux, the EMF is developed in this conductor, and therefore E2 is written as minus of M di by dt, where E2 is the EMF developed in secondary, M is the coefficient of mutual inductance, and I1 is the current in the primary or first conductor, where N2 is the number of turns in the secondary, N1 is the number of turns in primary, phi1 is the flux developed by the primary or the first coil, and phi2 is the flux linking in the secondary due to flux in primary or first coil. And hence, in other way, in terms of number of turns and flux, E2 can be written as minus of N d phi by dt. And here the number N is N2 and the flux is phi2. This magnitude is defined in terms of the parameters in second coil or the secondary coil. Now let the flux develop produced by the primary current linked with the secondary current, total flux, that is phi1 is equal to phi2. In that case we can say E2 is equal to minus N d phi by dt, and putting the value of phi over here, phi is equal to, we have already described what is the value of phi is. Phi is equal to mu I n into A upon L. Considering this equation, we are going to put over here, because this flux is due to the primary parameters, and hence it will be N1 I1 mu A upon L. Now rearranging this equation, it will give us minus of N1 N2 mu A upon L into di upon dt. Now earlier in case of self-induced EMF it was N square, but in case of mutually induced EMF E2 it is N1 into N2, whereas I1 will remain same because the current is in the primary which causes the EMF in the secondary. Now comparing the equation first and third, we can find out M di1 upon dt is equal to N1 N2 mu A upon L di1 upon dt. From here this constant term is nothing but equal to M, and M is the mutual inductance. Now this equation can be written as N1 into N2 upon S, because we know S is equal to L upon mu A, and putting this is L mu A, L upon mu A is nothing but S. Now comparing equation first and second, in case of first equation it was M di1 upon dt, in case of second equation it was N2 d phi by d phi2 by dt. Now comparing these two equations, it means this M1 I1 must equal to N2 phi2, and hence M1 I1 is equal to N2 phi2. From here we can derive the relation for M is equal to N2 phi2 upon I1. Now for the equation of mutual inductance, we are having two values. One it is N1 N2 upon S, another it is N1 phi2 N2 phi2 upon I1. Therefore the mutual inductance of the circuit depends upon the number of turns in the secondary circuit and the flux developed in the current and in the circuit and the primary circuit. Now we are having two definition for M. Considering these two concepts, here if we want to correlate between these inductance in primary and secondary or first coil and second coil, let me start from the basic. Phi is equal to Ni upon S and phi1 is equal to N1 I1 upon S. Similarly we can have phi2 will be equals to N2 I2 upon S, and S is the reluctance of first path and S2 is the reluctance of second path if these two paths are independent to each other. Whereas in this case we consider the flux developed in one circuit is linked with the secondary circuit, and hence either it is totally linked or it is partially linked. If it is partially linking, that component is taken as K. If phi2 is equal to K times of phi1. Phi1 is the flux in one circuit and phi2 is the part of that phi1 linking with the second circuit. And we know by the definition M is equal to N2 phi2 upon I1. This was derived from the previous equations. This is N2 phi2 upon I1. and here it is N2 phi 2 upon I1. Putting the value of phi 2 is equal to K times of phi 1, and by the definition we know phi 1 is equal to N1 I1 upon S, and hence M is equal to K and N2 N1 upon S. Now, the self-inductance of both the circuit, if it is one circuit, the L1 is equal to N1 phi 1 upon I1. If it is the second circuit, then it will be N2 phi 2 upon I2 by the definition of self-inductance of two coils. Now, in this case, putting the value of phi 1 over here, it will be N1 I1 S I1, and then it will become N square upon S. Similarly, in second circuit, if we are putting the value of phi 2 will be N2 I2 upon I2, then it will be N square upon S. When we consider the self-inductances of both the coil here is, one coil is this, and this is doubling magnetic field, and the another coil is this, the EMF E2 will develop in this coil due to the supply in first coil. Now, considering the same circuit and rearrange this one, equation 1 and equation 2, multiply equation 1 and 2, then it will be a L1 into my L2 is equal to N1 square upon S into my N2 square upon S, and hence we can say under root of L1 L2 is equal to N1 into N2 upon S. Now, on comparing with the other circuit, then we can say this N1 N2 upon S is nothing but N1 N2 upon S is nothing but M K times of N1 N2 upon S is nothing but equals to M, and hence we can say M is equal to N1 N2 upon S. Rearranging this equation, then upon rearranging this equation and putting the value of M over here, M is equal to, then it will be, we can say M is equal to K times of N1 N2 upon S. Putting the value of this then N1 N2 upon S is equal to M upon K. Putting the value of this function over here and rearranging the equation, we can find out K is equal to M upon under root L1 into L2. Here K is nothing but the coefficient of coupling, where K is equal to 1 means the total flux developed in the one circuit is directly completely linking with the secondary circuit, and there is no flux leakage. And K varies from 0 to 1, and 0 means there is no coupling between the two circuits. Two circuits are separately placed. One circuit is at this point and another circuit at this point. The field developed in this circuit is not going to link with this one. And K is equal to 1 means the circuit is completely overlapped. This circuit, one circuit, and this is another circuit, and both the circuits, the flux developed in one circuit is completely linking with the second circuit. However, this coupling may be varying between 0 and 1. Higher the value of phi 2 as a ratio of phi 1, then the better will be the coupling, magnetic coupling is. Now, there are some terms related with the flux. Flux linking, flux linkage, flux leakage, flux fringing. Flux linking. Flux linking here means the total magnetic lines of force in a magnetic circuit or field. Magnetic field is known as flux, and this flux passes through nearby conductor is known as flux linking. Means if there are some supply applied across this coil, the current is flowing I, it will develop a flux, and this flux, part of this flux will pass through this path, where some part of this flux will pass through within this area. This is the useful flux, whereas this is the leakage flux. It means it is not going to link with the another part of the circuit, magnetic circuit. This is known as leakage, and hence this is linking, flux linking. How much flux is developed and how much is linking with the another part of the circuit. Flux linkage. Linkage here means the rate of change. At what rate the flux is linking with the another circuit. Flux leakage. This is the leakage, which the partially this flux is not going to link with the rest of the circuit, and that becomes a leakage within this area only. Fringing here means when there is an air gap, these magnetic lines of force not passing straight way, it is changing its path, and effective length of the path of the magnetic lines of force will get changed, and this increase in effective length of this magnetic lines of force is known as fringing.